I've been asked today to talk about getting off gas. I've been a builder and energy rater for the best part of 2 decades now, and running a business to try and make it easy for people to live in a low impact, energy efficient, cheap to run home. And for half of that time, I would have been an advocate for gas, and I would be trying to put as many of my appliances as possible onto gas. But that had changed around 10 years ago. And now most of our builds are all electric builds. And our clients are having, really good outcomes, very low carbon, some of them are carbon positive outcomes running on all electric. So really today I want to talk about what has changed, and also to work through how getting off gas fits in with an energy efficient home when you're doing a new home or renovation or even a retrofit. So hopefully I'll cover most people's interests there. All right, so let's get into it. So remember when gas was green and air cons were bad? That's pretty much how it started back in 2001 when I started Positive Footprints. And it was all down to the fact, well, air cons were bad because they were very energy efficient then, high energy users. But gas was good in the sense that it was better than coal. In Victoria, we have brown coal, which is worse than black coal. It's less energy dense, so you get less energy out of it in the first place. We also have the issue that it's in the Latrobe Valley primarily, and there's a long way to transmit the electricity, and you lose around about 70% of that electricity or thereabouts just getting it to your home. So it's very energy inefficient. And in Victoria, we have the dubious distinction of being the state with the highest carbon intensity for our homes at 8.8 tonnes per year from the electricity and gas that we use. So electricity was bad. And of course, hence gas was better. And the reason gas was better is because it didn't have the transmission losses. You brought it to your home and you burnt it at source. And so we put it into our gas furnaces, our hydronic systems, our gas boosters for the solar hot water, gas cooktop, gas oven. If it could be gas, we'd pretty much make it gas. So what changed? So what changed for me, first of all, was the sustainability of it with the idea of fugitive emissions. This came around, it came to prominence around about 10 years ago. And it's simply the recognition that actually there are transmission losses in the gas network. And the transmission losses are not in the form of carbon dioxide, but in the form of methane. And methane is the main ingredient of the natural gas that we burn. And there's transmission losses all the way through the system, from when you drill down into the sedimentary rock to get at the gas that can often come up at high pressure, and it's hard to maintain a complete seal. Then in processing the gas, then in bringing it through the pipes and all the joins in the pipes, getting it to your gas meter. Gas meters can leak. I've often gone past gas meters and smelt that gas smell. And then incomplete combustion within the home. And the question is, well, first of all, with that methane leaking, the reason that's an issue is that methane is molecule for molecule 80 times worse over a 20-year period than carbon dioxide. And of course, it's this next 20 years that we're trying to get to a zero carbon as a world and as a society. So it becomes pretty important these next couple of decades. And how much emissions are there? Well, we don't know. And that's a little bit of a worry for me, especially since the gas industry has had a couple of decades to work it out, but has not pursued that. And there could be a good reason that they didn't want to know. Unconventional gas is now being pushed, and the reason that's being pushed is we sell a lot of gas overseas. In fact, we're the biggest exporter of gas in the world, second only to iron ore of our exports. So it's a huge industry, and we're actually now starting to run out of what they call conventional. That's conventional supplies. That's easy supplies of gas. Now we're looking at unconventional gas, which is more difficult to get. Requires more. Well, this one, coal seam gas, requires more drill heads to be put in, hundreds, potentially thousands over an area when they're getting the gas out. And to my mind, not only does that look like a more expensive way potentially to get gas, but also the opportunities for fugitive emissions probably will rise. Sounds logical. So at the same time as this idea of fugitive emissions making gas not so green came out, there's also a rise in the gas prices, and that's pretty much because we deregulated the gas industry and started to sell overseas. And overseas, there's a lot of demand, and so the price for gas domestically is competing with that overseas demand, and the price goes up there. This is a really interesting little page here that I found and wanted to show you. Of the gas exported, 72% of our gas gets exported, this big round ball there. But you look down here, the gas we use in our homes is only 3% of the gas that we use. Manufacturing is only 6.6%. So the vast majority goes overseas. And to take it overseas, they need to liquefy the gas so they can go over in tankers. And to liquefy the gas actually takes a lot of energy itself. And so the gas industry use gas to drive the liquefying process. And 7.5% of the gas that we mine actually goes towards that process. And it's a little bit sad for me that since 2005, we've started as a country putting in a lot of wind farms, solar farms, and a hell of a lot of rooftop solar, and I've been sort of pushing that. And the electricity grid has actually responded and started to become more green, in the order of about 15 million tons of carbon dioxide less intensive than it was in 2005. But that gain in carbon efficiency, I guess, has been completely offset by the fact that we're now burning a whole lot of gas to send overseas. So anyway, those are the issues with gas. And at the same time, the technology has moved on, and the air conditioners, which used to be the big bugbear of the sustainability movement, you wouldn't want to call yourself a sustainable builder and have air conditioners in your home. These are now the darling, because they now have inverter technology and they are much more efficient at what they do. In fact, they're so efficient that they can be more than 100% efficient, 200, 300, 400, 500, and most efficient are 600% efficient. What do I mean by that? So I'll give you a little, this is sort of a little section of what an air conditioner looks like. Now, there's different words actually for this. Some people call them split systems, air conditioners, they're a type of heat pump. All of those words mean the same thing. But the reason that they can be so efficient, if you think about, say, a gas burner trying to produce hot air for a home, the most efficient that it can ever be is 100%. If all of the burning turns into heat, all that heat gets ducted into the house and none of it escapes out the ductwork, 100% efficient. That's because it's making heat. But these heat pumps aren't actually making heat. They're just running a transport network from the outside to the inside around this sort of loop. And they're running a refrigerant to do that. And as they're running, what they're doing, the refrigerant gets very cold on the outside. There's in heating mode, will get very cold, will run through these pipes, very, very cold, maybe minus 40. They'll blow air across it. The air will transfer heat from that air. Now, that air might only be 5 degrees, but compared to minus 40, it's still very warm. Transfers its heat into the refrigerant. The refrigerant goes up to the indoor unit. It gets compressed. That heat comes out and goes into your room, and it just runs this round and round. In cooling mode, it'll run the opposite way and grab heat from the inside and shift it outside. And in doing that, a system like this might use, say, 1 kilowatt hour of energy to circulate. But in doing that 1 kilowatt hour of energy circulating, it might be able to transport 3 kilowatt hours of heat or 4 kilowatt hours of heat, or the best are up to 6 kilowatt hours of heat. And that factor of improvement is called the coefficient of performance. So if it's shifting 5 kilowatt hours of heat for every kilowatt hour that it runs, it's got a coefficient of performance of 5. This is important to know because when you're buying, that's a number you should be looking for. What's its coefficient of performance? The higher, the better. There's also another number that you should be looking out for, is the energy efficiency ratio. And this is just in cooling mode. How efficient is it? And it'll be a very close number, but they have slightly different efficiencies, whether it's running forwards or backwards. So it does, you might notice here's a hot water system, looks the same sort of thing. Again, it's got a compressor motor, and this time it's just shifting heat into the hot water tank and just running a little circulation through those two pipes there. This is one, we put in a lot of these, but there are a lot of different heat pump hot water systems. This one's called a Sandon. It has a coefficient performance of around about 4.5. Means for every kilowatt hour of energy that you use, it shifts 4.5 kilowatt hours of heat into the tank. So heat pumps are sort of like, you can think of them like the LEDs for the heating and cooling world. It's that sort of factor of improvement over what we had. And at the same time, another piece of technology that works very well with going all electric is the fall in PV prices. My first PV system was a 1.5 kilowatt system back in 1998 when I lived in South Australia. It was 8,000 after government rebate for 1.5 kilowatts. These days, well, here's one I just pulled off the internet. So you can get very, very cheap prices for large systems. And what do you do with that energy? Well, in the middle of the day, if you're all electric, you can put it into your hot water and heat the tank. You can put it into heating up your home. And of course, if you've insulated your home well, when the sun goes down, you can turn it off and the house should maintain its heat well into the night. And the same in summer. You'll be making heaps of power in summer. You can use it to run those air conditioners. And again, once the sun goes down, turn it off and retain that coolness if your house has been designed well. We'll talk about retrofits in a minute. And what sort of outcomes can you get? So this is a house we built a few years ago. We've looked at the energy data. This is a new home. It's 8.1 star, so it's a well-designed house, I believe. It's got a 4.8 kilowatt system. There's 3 adults who live in this house. Most of the time they're working from home, and they average 0.6 kilowatt hours a day from the grid. So just about carbon neutral over the year. That doesn't mean every day it's like this. Some days they'll be drawing energy from the grid. Some days they'll be putting more energy out into the grid from their solar, but on balance, 0.6 kilowatt hours a day. This is a renovation that we did. So renovations can also have a really good outcome. This one uses 3.3 kilowatt hours a day. Very low levels, considering there is no gas in these homes. It's just electricity. The way that we achieve this, by the way, with a renovation, it's reasonably easy when you know what you're doing to do a sustainable extension. But to get a good performance on the whole house, it is important that you also put some effort into retrofitting the existing part of the house, if there's any money in the budget to do that, to insulate and say double glaze, so that existing part of the house can also perform well. Oh, did I go the wrong way? Did. Okay. And to put it into some sort of perspective, this is a pie graph I like to use to give people an idea of where to head and what areas to address to make their homes perform better. And so this is the average house in Victoria. If you looked at all the existing homes, you added up their energy use, this is sort of the pie graph that you'd end up with. You can see most of the energy goes to space conditioning, and most of that, I'd say 4/5 of that is in heating, because we're in a heating climate where we're cold most of the year. A significant amount goes to water heating. You've got general appliances, and you've got cooking and lighting. So that's sort of the breakdown. This pie represents 8.8 tonnes of carbon dioxide, as I mentioned, for the average home. but it also represents, if you combined your gas bill, converted it to kilowatt hours from megajoules, and you combine it with your electricity bill, the average home uses 52 kilowatt hours a day. So that just puts in perspective what you can achieve versus what is currently the norm, if you like, or the average. So I've come up with this thing called a roadmap to carbon zero homes, and this is just a useful device to show where the big low-hanging fruit are to grab, and what the effect of implementing different strategies is on the improvement to the pie graph versus the average house. Whoops, gone the wrong way. So when you're looking at space conditioning, whether you're doing a new house, a renovation, or retrofit, there are three things that affect the performance or the amount of energy that goes into space conditioning. One is house design. Obviously, in a retrofit, you don't have the benefit of mucking around with that too much. The next one is building to make sure that the house performs as it was designed to perform. And the last one is the energy efficiency of the heating and cooling that you put in. So my first tip is, if you're doing a new home or renovation, what you should be doing is aiming for what they call a NatHERS rating, or a house energy rating of 7+. So new homes have to have an energy rating, and the minimum is 6. Just on that scale, a 0-star house would be like a tent. A 10-star house is a house that theoretically needs no mechanical heating and cooling. I would say don't go for the minimum, go a little bit higher, try to get to 7. It just makes it very easy to have a really good performance for the whole house as we try and minimize the wedges of those pies. The other thing I would say is this little guy down here called TPA, Thermal Performance Assessor. This is someone who does the rating. I'd get them involved at the design stage, and this is what we do when we do our designs. But 99% of the industry don't do it. They'll use it as a compliance tool just before you get the building permit. Unfortunately, at that stage, there's very little that a house energy rater can actually do to improve the design. All they can do is insulate the walls if they're not already insulated, or bump up the insulation levels to the maximum that will fit in the cavity, then start double glazing windows. And typically they'll get to 6 stars and stamp it and just send it back. And it's sort of a recipe for minimum compliance. But the value of the software is you can actually play with the parameters in the room. You can make windows bigger, smaller, introduce more mass, higher insulation levels, change the eave depth, and you can tweak each room of the house. And in doing that process, going around tweaking each room of the house, while it's still at a fluid design concept stage, you can quite easily, well, not quite easily, but you can often improve it by around about 1 star in performance. And that's even when you've designed it with passive solar design in mind. Passive solar, by the way, is just using the sun, getting the sun in winter, at least in the Victorian climate, getting the sun into the house in winter in many places as you can, keeping it out in summer with decent eaves, maybe getting some breeze paths blowing through, connecting it with some mass, connecting it to the earth so it's quite a stable temperature, and just working with the local climate so it doesn't need as much energy to heat and cool. All right, so if you do that, even if you get to 6 stars here, this is the 6 stars minimum, compared to the average house, a 6 stars new home, as long as it is built well, a 6 stars new home can, makes a reasonable difference compared to the average home. Now, the average home is around about 200 square meters. Obviously, if you build a huge home, your size of wedge here will be a lot bigger. However, there's a 6-star home, a 7-star home. If you build it to a 7 stars performance level, you get a bigger impact on your space conditioning. Then 8 stars, 9 stars, and 10 stars effectively removes that component of your energy load. So it does have a big impact. So for those people doing new homes renovations, consider that. For those people who are doing, who just want to retrofit their home, unfortunately, you don't have that luxury of redesigning your home. So I would focus instead on trying to get it tighter and well insulated, and just do the easy things. So stop unwanted breezes. These are things that you'll probably already know where they are in your house. So when it's windy, where do the breezes, when you're walking near the external walls and doors and things, where do you feel those breezes? And try and stop those. You stop those with weather sealing of your doors and weather seals at the bottom, weather strips around the frame. A lot of homes will have these internal vents on the room walls. We no longer need those. Those were put in back in the day when we had gas heaters that weren't flued to the outside, and that was to stop you getting methane poisoning if you got unburnt gas. So these days, heaters are flued to the outside. If you're not sure, ask a builder or a plumber before you close these up. But on most homes, you should be able to close those up and stop that air leakage to the outside. Extraction fans is another one you want to look out for. This is very common in bathrooms. They're just holes through to your roof. So your hot air in winter is just going to be rising up there to your colder attic space. In summer, you might get, hot air coming down when you don't want it. So just put one of these over the top and it just closes it off when it's not in use, and then opens when the air's blowing. And of course, you've got chimneys. You can put dampers on. You can seal up the throat of the chimney as well. So it really depends on the house what you do. But the point is, find your gaps and cracks and just seal those as a first instance. This is even before we talk about getting off gas. The other thing you should be looking at for an existing home is insulating easy spaces. So, you might not want to re-insulate your walls. That might be difficult, but ceilings definitely. Go up into your ceiling, measure the depth of the insulation you've got up there. If you've got less than 200 mil of depth, I'd be putting another layer of insulation over the top. 200 mil is equivalent to an R3.5 bat, which would probably be my minimum that I'd recommend. One thing to note, though, from a safety point of view, is that you must, before you cover over like this, if you've got downlights that go into your roof space, those downlights can only be covered over if the lights themselves are rated at IC or ICF and say abutted and covered, or have a symbol that shows that. Otherwise, by law, they need to have the insulation pulled back so that the light globes don't overheat and cause a fire in your roof space. So be sure that you've got the right sort of downlights. If you have downlights, if you've got pendants hanging down, everything should be fine to do this. And if you're building a new home, just try and avoid downlights to begin with. You can insulate under the subfloor as well, as long as, again, you've got enough height. 400 millimeters of height you really need for someone even to consider going under there. It's not an easy task lying on your back putting on underfloor insulation rolls. And again, I'd suggest an R2.5 roll to go under there. Now, wall insulation, I think it's worthwhile doing, but I would only do it if your weatherboards or your cladding is failing or rotting and needs replacing, or as part of a renovation process. And when you're doing it, change over your windows at the same time, and it makes sense to do that. Okay, so let's see, assuming you do some of those things, it's very unlikely as a retrofit you'll be able to do all those things. You might find, your house has improved a little bit. You've made a bit of a dent, but it's not going to be at new house standard, probably, unless you're able to do a number of those items. But don't despair, because you can still do a lot with technology these days. So the next thing to look at is to, if for existing house, change over your heating system to an aircon system now that you've insulated what you can and made your house sort of reasonably tight, or at least got rid of the main offenders. If you're doing a new house, just use these from the beginning. And I'd be specifying a coefficient of performance of greater than 3 is what you're looking for. Typically, most of the ones that we put in are 4+. If you can do that, effectively, if you've got a coefficient of performance of 3, what it means is, if this is the amount of heat that we need, or heating and cooling that we need, and you've got a coefficient performance of 3, effectively you can provide that with 1/3 of the power. So like that. So, you made a significant cutout from the average house compared to what your house is now. And of course, if you're a new home, that wedge would probably already be smaller, because you'd be starting at a lower, well, you would have already cut off more in the original design and construction. Multi-splits, by the way, split systems can also come as multi-splits, where you've got one compressor to a number of heads. They don't have to be the ones up on the wall. They can be roof cassettes. They can be built into bulkheads, so it just looks like a grill, more like a ducted system would look, or they can be radiator panels. You can put them in as ducting through the roof, like more like a standard system. However, it will not be as energy efficient, just like any ducted system has reasonable inefficiencies because it's going through a cold roof space and you lose a lot of heat into your roof, even with insulated ductwork. There are also hydronic systems. For those people who like hydronic systems, you can get heat pump boilers that are very efficient these days. Of course, hydronics only does heating. It'll only do the heating component. It doesn't do the cooling. So if you do want cooling, you would then also put an air conditioner up on your, up like they've done here. And that potentially that air conditioner could really do the heating as well. All right, so what do you look for when you're buying an air conditioner? Like I said, the main things you should be looking for is this COP EER here, energy efficiency ratio, coefficient of performance. And here we go. I'm looking at this set here. That'd be the number for the indoor unit and the outdoor unit bit that goes on the outside. This one is the best on the market with a coefficient performance of 5.81. That means for every kilowatt hour that I run it, I transfer 5.81 kilowatt hours of heat or cool if it's in cooling mode. Well, actually cooling is a bit better. It's actually 5.95 for cooling. So look at that. The other thing to look at is that I think is really important is the refrigerant type, R32 here. The reason that's important is those refrigerants are also greenhouse gases, and they're typically a lot worse than, well, even than methane, than carbon dioxide. So I've got a table here. The average air conditioner has about a litre or a kilogram of refrigerant in it. Now, the best for air conditioners at the moment is this R32. If that refrigerant, if that at the end of its life, if it gets thrown on the, on the tip and that refrigerant is allowed to just dissipate to air, that 1 kilogram of refrigerant will be equivalent to 675 kilograms of CO2. And that's the best on the market. Mostly what's on the market now is this R410A. So that could quite easily be 2 tons of carbon dioxide equivalent if you are just dumping your system or not decommissioning it. So old systems must be decommissioned. So if you are changing over or getting rid of a reverse cycle air conditioner, you need to get someone in, a plumber in, to decommission it properly and to capture that gas. And of course, if you're doing a retrofit, make sure you you can recycle your old gas heater. It's mostly metal, so you can potentially get some money for it as a scrap dealer, or you can take it to a transfer station, or maybe even the council pickup service. All right, so that's space conditioning and everything you sort of need to know to make a big impact there. The next section to look at on this pie graph is water heating. So what can we do there? Again, there's two factors this time. One is how water efficient are the hot water appliances in your house? That depends on that factors into how much hot water that you need. And then how efficient is the hot water system that you use? So if we look at the water efficiency first, the 2 things to look at, first of all, is your shower. Your shower uses half of the hot water in your house, goes to your shower. This is really a dead set winner. And I think if you're retrofitting your house, I definitely do this straight away. Not only will it save water, but you'll start saving energy and they'll be reflected in your bills from day one. The other appliance to look at that uses a lot of your hot water is your washing machine. And this, because it's a more expensive item, I would probably just change it over when you need to change over your washing machine. But definitely for a new house, if you're getting all new appliances, you want to go for one that is very energy efficient and very water efficient as well. So what sort of impact will it have? Well, if you can go for what they call 4A shower head instead of the standard 3A, you save around about 15% of that little wedge there. If you can go for a water efficient washing machine, front loader with a few stars, you'll save a similar amount, a little bit less. But together, that's about a third of your hot water needs that you don't need anymore because you're more efficient at what you do. The next bit of the wedge, you can minimize that by, again, turning to heat pumps. So like I said, the Sanden that we use has a coefficient of 4.5. We set ours to daytime heat for two reasons. One, it's easier to get heat out of warmer air than it is out of cooler air. The compressor works a little bit better. And also, if you put photovoltaics on your roof, then you can set it just to run and turn on during the daytime so that you're using that solar power, like I mentioned before. Just as an aside, check the plumbing. Plumbers don't necessarily think about looks or energy efficiency. So once you've had a changeover, if you're doing a retrofit or even a new build, just check and caulk the penetration so you don't get unwanted air going in and out of those. So if you do put on a heat pump hot water system, typically you'll get, if it's a COP of 3, once again, you can provide that amount of hot water with about a third of the energy. If it's a COP of 4, it'll be a quarter of the energy, a bit less. But you can straight away see we've made huge impacts already, and this can even be with an existing home, on the energy usage in a house. The next step, lighting, is a pretty easy one. And it's really just, if you haven't already changed over to LEDs, change to LEDs. For a new house, just use them from the start. Make sure, of course, you're insulating them. Like I said, you use the right sort that can be insulated over. If you're building a new house, I would actually move away completely from LEDs because they introduce penetrations in your plaster and you get a leaky house. So you want to try and minimize holes in your plaster. Pendant lights like this are much more efficient. They'll be cheaper for the electrician to put in as well. If you do that short little measure, you can expect about a 30% gain on that section of the wedge. For cooking, now, this is often, once you've been through this process, this is often the last appliance in the house that uses gas. Now, it doesn't actually use all that much gas. It's only a small wedge. But the good thing about it is if you change to an induction cooking, first of all, is about 50% more efficient than a gas cooktop because a lot of gas goes up around the sides of your pan. So it's more efficient to begin with. But the real benefit is that if you don't have this, you probably don't need a gas meter, and that'll save you around about $300 every year in connection fees. You can just get them to disconnect the gas meter completely. If you do that measure, again, you get a little bit of a benefit, but the benefit is getting rid of the gas meter. If you must have your gas cooking, don't feel too bad. It was only a small amount, but it's an opportunity to save a fair bit of dollars. And the last section is really just to look at appliances. And for appliances, my rule of thumb is really just change over to efficient appliances at the time when they break down. The only one I might say is fridges. If you've got a very inefficient fridge, they use so much power that you probably should, you might want to consider changing over to those. Now, they have different amount of stars. So this is just to guide fridges, TVs, and dryers all go up to 10 stars. Just bear that in mind when you're going and comparing models, whereas your dishwasher and your washing machine and your aircon go up to 6 stars. This is all just to confuse us, I'm sure. But again, if you choose, or if you're doing a new house and you're choosing more efficient appliances, over time you can expect, if you work through that list, you can expect a reasonable discount in your appliance use. I'll just go back to this. This is just a breakdown just of appliances, and it just shows, refrigerators are really one of your number one things to think about. TVs, those big TVs can also use a lot of power. So that might be another one to really focus on there. If you do have a pool, again, pools can use a lot of power. So make sure your pumps are as efficient as they can be. All right, so we've really minimized this pie as much as we can. How am I going for time here? Okay, not too bad. I'm nearly there, Steph. Really the last piece of the puzzle here is to then think about photovoltaics. And if you're doing a retrofit, look, I would probably be putting on photovoltaics as soon as I can, just because the cost price is right, and they can contribute to so many things around the house, the power. So anyway, this is just a picture of the first house that I had, that the clients sent me the bill and said, we're using much less power than we need, or we're producing much more than we need. Just a couple of things to consider if you're putting on photovoltaics is shading. So a lot of the cheaper systems, they'll just be the standard system where all these panels are just in series. When something's in series, if one of the panels goes down because it's got a shadow on it or is not producing as much power, it will block the power from all the others in the same series down to its low level. So take into account shade and try and avoid shade. If you can't avoid shade, instead of a standard, what they call a string inverter, I would be going for these micro inverters. They're little ones that go on the back of each panel. And so if one panel goes into shade, the others keep performing. There's another technology called a solar maximizer that does the same sort of deal, but ask the installer. And this is really important too. Try and choose an inverter that comes with software so you can monitor it and find out where you're using the power. If your inverter doesn't have that, there are systems, this one's called Solar Analytics, that will clip on, they've got like a little clip-on meter thing that will give you the same reading back. This is just super important because it tells you whether your panels are working or not, because how would you know otherwise unless you're always checking your bills and correlating that with the weather? Solar Analytics, in fact, will send you an email if your panels aren't performing as they would expect them on any day. And it's not uncommon for panels to stop performing. So you want to pick that up sooner rather than 10 years later. So if you do offset with photovoltaics, just what I've found from my clients, somewhere around 5 kilowatts a panel tend to be the place that starts getting towards producing as much power over the year as what you use over the year. So that pretty much gets rid of all your loads. You will still be drawing in energy, at nighttime, obviously, when there's no sun, unless you get a battery system. You'll be drawing energy from the grid. It won't be very much. So I would suggest, if you want to go that next step, is just to make sure that you're choosing green power when you're looking at energy providers. Ask them, do you have a green power program? And that way they're required to source their energy that they supply to you from solar or wind farms. And that effectively takes it all away. And congratulations, you are now at gas-free, low-carbon living. That's pretty much it, Steph. Oh, I should just say, if I can do a quick plug, we've recently brought out a range of carbon zero homes. So they are already fitted with the most efficient appliances that we could find. And we put enough solar on there to not only power the house, but also power an electric car, should you get one. We put in the infrastructure for that. And also produce a little bit more, so that over time, even the embodied energy in the materials that went to make up that house is slowly offset over time. So there you go.